pond in this question is in the shape of a hemisphere. It has radius 5 meters and water is in the pond to a depth of 1 meter. The hemisphere has a radius of 5 meters. But that's not the only place that we can see a radius length in this diagram. The radius is anywhere from the very centre of the sphere to the outside surface, so this length here is a radius as well. It's also 5 meters. Now currently the water level is 1 meter, and so that means the distance from O to A will be 5 meters minus the 1 meter, or 4 meters. Part A asks for the length of the water line, and that's the length around the surface of the water, and I've drawn a circle to represent that water line. There is a point L on one side and point M on the other side, and point A is right in the centre. We also have a triangle marked out inside the diagram. It has a point O, point A, and point M. So the length across the bottom of the triangle is the radius of the waterline surface. We know that the distance from O to M is 5, and we worked out before that the distance from A to O was 4 meters. So we can use Pythagoras' theorem to find the radius of the waterline. 5 squared equals 4 squared plus AM squared, and so AM squared is equal to 5 squared minus 4 squared. That's 25 minus 16, or 9. So the length from A to M is going to be the square root of 9, or 3 meters. Now the length of the waterline is the circumference of the circle with radius AM. So the circumference can be calculated 2 pi times the radius AM. We calculated that earlier as 3 meters. So the distance around the waterline is exactly 6 pi, but we can round it to 2 decimal places as 18.86. meters, correct to 2 decimal places. The area of the water surface is equivalent to the area of the circle that is the surface. We can use the simple area of a circle rule, pi times the radius squared, the radius being that distance from A to M. That was 3. 3 squared is 9, so the area is approximately 28.3 meters squared. That's rounded to 1 decimal place. In part C, we're going to find the shortest distance along the surface of the sphere between L and M, and that's going to occur on a great circle of the sphere. The great circle is going to look something like this. It will come around the surface of the sphere joining L and M, and then continue up and over the top of the sphere and back around. And this is the circle that we'll use to calculate the arc length, which is the distance between L and M. So here is that great circle, and the points L and M will be in this approximate location. The centre of the sphere is here, and we have a radius from O out to M of 5 centimetres, and from O to L is also a radius. The distances are actually in metres, so that's 5 metres. We also know another point A that is in between L and M, and we know that that distance from A to M, as calculated earlier, is 3 metres. We can use some simple right-angle triangle trigonometry to find this angle here. That's the angle AOM. We know that sine of that angle is equal to opposite over hypotenuse. That's 3 over 5. And so the angle AOM, once you work that out on the calculator, is approximately 36.87 degrees. Now, because the angle LAO is exactly the same, the angle LOM is twice angle AOM. So that will be 73.74 degrees. So the length from L to M along the great circle will be equal to pi times the radius, which is 5, times that angle that we just calculated, 73.74, divided by 180, for a final length of approximately 6.44 metres.